All right, hi everyone. Welcome to this session on extreme precipitation, past, present, and future. Wow, off to a great start. Okay, we will get started just a moment here. We've got a great set of talks lined up for you. Oh no. Okay, apologies. I started hearing myself in a delayed echo. Hopefully you can all hear me very well. Let me bring up. Okay, I would like to start by noting that we have several talks here today. We also have two presentations that will be given in the poster session that is Wednesday from 12:15 to 1:50 Eastern time. So I would encourage everyone to go check those out. There's one on framing extreme precipitation events in the context of cumulative emissions, and there's one on non-stationary estimation of IDF curves based on high-resolution simulated precipitation. So with that, we will get started with our first speaker. And a reminder that you should put any questions you have into the Q&A box on the event platform, and I will present those to the speakers, time permitting. Our first presentation is Ruping from the Meteorological Service of Canada. Go ahead and share your screen, and you can start your presentation.
You see my screen?
Yes.
Okay. Let's see. Okay, good day, everyone. So my talk is about atmospheric river analysis. It's related to heavy precipitation. So I would like to thank my co-authors. I'm a senior meteorologist with Environment Canada. So I'm working in Vancouver. So here's atmospheric river is the main concern, mainly in the winter season here. So we'll go quickly with the outline. So I'll go through, talk about concept of atmospheric river and some definition, and how this atmospheric river can relate it to extreme precipitation. And then I will propose two moisture adjusted flow quantities that can be used to assess the impact of atmospheric river, mainly for precipitation. Then I have a summary for that. So atmospheric river as a weather phenomenon, so can be defined, generally defined as a long, narrow, and transient corridor of strong horizontal water vapor transport. So this system is typically associated with a low-level jet ahead of a cold front of the extratropical cyclone, and the moisture flux can transport moisture from the tropical or sometimes just extratropical moisture source. And the landfalling of AR can lead to heavy precipitation and severe flooding. So here you can see that some flat conceptual model of the atmospheric river. So this is the top here is flat pattern of the atmospheric river. So this is strong cold front, and then this is a low level jet, so ahead of the cold front, and this is a extratropical cyclone. This is a typical pattern of the atmospheric river. And then you can see that vertical cross section, you can see this cold front, and then upper level jet and lower level jet. So this is the atmospheric river system over just ahead of this cold front in the lower stratosphere. So this is so for atmospheric river analysis, because that definition is a strong horizontal water vapor transport. So usually we use this integrated vapor transport, so define it by this formula here. to analyze and identify the system. This is a related quantity called integrated water vapor, or sometimes we call it principal water. So that's the moisture available in the air column. So it is integrated from surface to the top of the air column. And there's another quantity we are going to use. This is called column relative humidity. The idea is that if the air column is wet, that can be easily generated precipitation. But if it's dry, then even you have a strong water vapor transport, you may not get too much out as precipitation. So this is column relative humidity, so defined by this formula here. So this ISWV is integrated saturation water vapor compared with the just integrated water vapor. So this is the maximum water vapor can be available in the air column. So this variable is generally smaller than 1 and then greater than 0. So for AR analysis, so this is general water pattern equations. If you do this vertical integration, you can get a relationship between precipitation rate and evaporation, and this is moisture, the change of moisture in the air column, and then the change rate of condensed water in the air column. The dominant terms come from this water vapor conversion of water vapor transport. So you can see that precipitation rate can be proportional to the conversion of water vapor transport. So the idea is that we use IVT to define Adams River, but its impact is associated with its conversion, not to the IVT itself. So there's a system called atmosphere river scale. Usually people use this to categorize the intensity of the atmosphere river. So this is a very popular scale currently used in atmosphere river analysis and prediction. So it categorizes an atmospheric system as category 1 as a primary beneficial event. So this system is based on the duration of atmospheric river and the intensity of the atmospheric river. So intensity is based on the maximum IVT magnitudes at a location. So the idea is to better categorize and communicate the strength and potential impact of landfalling atmospheric river. So studies have shown that the insurance loss due to atmospheric river can be exponentially proportional to the rank based on this system here. Now the idea is here we try to introduce the pseudo IVT that is just applied by this equation here. The idea is that as I mentioned earlier, if you have an air column, it's the wetness of the air column is measured by this column relative humidity. So it's kind of if we multiply this term on the IVT, it will increase the intensity of the system if the air column is wetter than average. So this RM is a kind of average of air column humidity. So if it's drier than average, then it will reduce the amount of IVT. The expectations that this pseudo IVT should have a higher correlation with precipitation rate than just IVT. so here is an example showing the case of west coast of Canada in November 21. So we get a big storm and flooding in southern BC here. So the top panel here is just IVT. You can see that compared with the PIVT in the bottom panel, you can see that PIV is much stronger at the center there compared with IVT, just IVT over this region, because this region is already quite wet. So we use this adjust IVT, so you can get enhance over these areas. And in some other area, you can see that in the higher latitude, you can also get some. So this top here, I said, is IVT, but the blue counter is PIVT to 250s. So here's some correlation, as I mentioned, that we expect that PIVT has higher correlation just based on this case here. We have I use 3 statistics. This Pearson correlation, and Spearman and Kendall correlation statistics. The idea is that Pearson correlation is related on the normal distribution of the quantities, but for both total precipitation rate and IVT, they are not normally distributed. So maybe these two statistics is more robust. You compare this compare with these two quantities. So you can see that PIVT has much higher correlation with precipitation rate compared with IVT here. Before I go get some more statistic based on more data, I will go with give another definition or another quantity we introduced in this study called pseudo moist flow. So it's based on a moisture weighted average, moisture weighted mean flow. We can define it by this formula. So IVT divided by integrated water vapor. So that is moisture weighted mean flow. And then if you multiply by this integrated column relative humidity, so we get this, we call it pseudo moisture flow. So it's kind of a variant of pseudo IVT. So you can compare these two panels here. So this on the left here is moisture weighted mean flow. And then if you apply this multiplied by column relative humidity, then you can, it kind of give you the shape of atmospheric river. So you can use this. The idea to use this because you can relate it to lower level moisture jet, so they have the same unit as the wind speed. Okay, so here is the correlation between IVT and total precipitation rate based on 45 years data, 4-time daily data. You can see compare with correlation with PIVT. PIVT. You can see that PIVT have much higher correlation compared with the if you just use IVT to calculate the correlation. And also we can see that pseudo moist flow also have some high correlation compared with the IVT, but only this Pearson correlation is lower. Okay, so let's try to get some application for this. One application, we can use this PIVT like, to define the shape of atmospheric river. So this is usually people use just use IVT 250. So this is the at this blue no this color up as atmospheric river, but with this PIVT we have that adjustment based on the saturation of the air column. So it may have better, it's more related to the impact of the atmospheric river in terms of precipitation.
You have less than a minute left, please.
Okay, so this is you can see that this tool, this much stronger PIVT here, and the other application is used to do this AR scale. So this is idea. You can see that for this case, based on the IVT, it's categorized as a strong Cat 3 atmospheric river. But if we use a PIVT, we can get this as very strong. It's a category 5, exponential, exceptional strong atmospheric river for this case. You can see that here is Highway Canada. It's not river, but there's the flooding of that event. Okay, so the summary is here. We try to, for atmospheric river, IVT is the most appropriate quantity for AR identification and intensity rating. But here we introduce two pseudo variables, just try to get better reflect the impact of AR on precipitation. Yeah, okay.
Great, thank you very much. A reminder to everyone listening, on the event page for this session, there is a chat and a Q&A tab. Please put any questions you have for the speaker in the Q&A and I can read them out. There is one question which we will try to answer quickly. Are correlations you showed regional mean correlations, and which domain was used?
That's the global domain. So the average, so the correlation is based on the global domain data. And then we have some weighting based on the latitude of the grid point.
Excellent, thank you very much. I think we will move on to our next speaker. Note there is that chat box as well if you want to continue conversations about any of the presentations that could happen there. All right, thank you so much. Our next speaker will be Alissa Steeves from Environment and Climate Change Canada. Alissa, you can go ahead and start sharing your screen.
It should be sharing now.
Yes, it looks great.
Okay. All right. I'm just hoping that that stuff at the top goes away. Okay. Hello, everybody. My name is Alissa Steeves. So yes, I do work for Canadian Centre for the Meteorological and Environmental Prediction, formerly known as the Canadian Meteorological Centre. So last year after this event, I went ahead and started a case study, and there's quite a bit of interest generated. So the research and development, primarily the development unit, got involved. So I'd like to acknowledge some individuals from that group, Cheung, Marc Verville, and Manon Fauché, for some of the work they did thereafter that I will present as well. So. Okay, there we go. So the synopsis for the case doesn't look like much meteorologically on the left. It's, there's an area of low pressure kind of moving into Quebec, and it's basically got the Maritimes in the warm sector with some southerly flow off the Atlantic Ocean, primarily going into Nova Scotia. The middle image there sort of demonstrates it's an image of precipitable water being funneled in that southerly flow directly across central Nova Scotia, actually across to PEI and into the Gulf of St. Lawrence thereafter. And then on the right-hand side, there's a radar image, I think it's once every hour, showing some pretty intense precipitation radar echoes related to that. I guess we can call this an atmospheric river being funneled in by that what looks to be relatively light southerly flow. And this kind of went on for about 48 hours, more or less. There was a bit of movement east over time, but very, very slow. And there were extreme rainfall rates across central parts of Nova Scotia during the evening of July 21st, which is what I'm going to focus on. So looking at some of the impacts, I'm going to get to the observations on the next slide, but there is a radar image there, just showing kind of some of the observations that went behind this. That was the morning. That was a 24-hour radar image. So it's suggesting, the radar output is suggesting amounts exceeding 300 millimeters in the 24 hours between Halifax, which would be, this is the Halifax area here, and then Windsor, just south of Windsor, Nova Scotia. So really good access of high precipitation values. So in terms of impacts, 4 people died. There were hundreds of repairs needed on roads, driveways, bridges. You see the train track here washed out. That was basically the connection from Halifax to the rest of the country to the west. There was actually a state of emergency declared that the 22nd, which was the Saturday, and it lasted for 2 weeks. And you can see some of the flooding in one of the areas that experienced some of the highest observed rainfall in Bedford, which is basically part of the Halifax metropolitan area to the northwest, on the northwest side. So in terms of some specific observed rainfall amounts, focus would be, again, there was the axis kind of came through here. So we have Hants County. There were some amounts exceeding 200 millimeters there. There's an isolated observation a little bit further east. There's a really good gradient over the Halifax area. So again, I mentioned Bedford to the northwest, they observed 230 millimeters, but then over towards Dartmouth, it was less than 100, and then down, trying to remember where that is, down the coast a little bit further to the southeast, they only reported 23 millimeters. And then over in Bridgewater and Liverpool, again, we see amounts exceeding 200 millimeters, and this is all it's maybe a little more than 24-hour totals from like the entire window. This was measured at noon the next day. A lot of what I've got is going to be from 8 a.m. or sorry, 9 a.m. local, 12 Zulu on the Friday to 12 Zulu on the Saturday. So it's a little bit further down the road, but there was a maximum amount, observed amount in Bridgewater of 262 millimeters. There's a peak 1-hour rainfall rate of 95 millimeters in Upper Falmouth, just west of Windsor. So some pretty, really intense. And I recall I showed that area where it was potentially exceeding 300. There were unfortunately no observations in there to corroborate the radar, what the radar was seeing. So looking at the NWP forecasts, the model deterministic forecasts, it left a lot to be desired, to say it straightforward. Certainly most of them, I would say probably maybe not so much the GFS, but all the others suggested some pretty decent amounts. You can see the scale there, exceeding 50 millimeters, sure. Some of them even put over 100 millimeters, getting into the purples, particularly UK Met, but had a good area of that west of Halifax down to southwestern Nova Scotia, and even up towards Windsor is actually over here, but it did sort of hint at that really extreme axis. ECMWF had a couple of bullseyes of really good amounts, but and they were kind of around the Bridgewater, Liverpool area, I believe, but again, missing that axis going up towards Windsor, it certainly dropped off towards Halifax. So, and I mean, even though it was exceeding 100 millimeters, we were talking about amounts exceeding 200, maybe even 300 millimeters, and there's nothing to that effect seen here. So looking at the Canadian models in particular, depending what you're interested in, GDPS on the right, the lowest resolution of the 3 to 15 kilometer, it did suggest amounts pushing 150 right along the coast. But as I showed, those amounts definitely came inland, they weren't just seen along the coast. RDPS was particularly problematic. It had a little bit of a bullseye down in southwestern, but for the most part, otherwise, it was keeping amounts generally less than 75 millimeters during the period. HRDPS, the high resolution 2.5 kilometer grid spacing, did have a better, I guess, distribution. It did certainly put the higher amounts further inland, but again, still left a lot to be desired with a bullseye again, reasonably well placed bullseye, but only peaking at 106 millimeters. And to be clear, this is all not post-processed raw model output. And just to do a bit of a comparison for 1 hour between radar and forecast, you can really see the problem that the models just are not sufficiently handling this convection. So this is these are using the same color scale, which of course I've forgotten to put here, apologies. But we have a really good radar echo showing a bullseye, for example, of 51 millimeters in 1 hour across Halifax. This is between 22 and 23 Zulu on the 21st. The equivalent 1 hour outputs from the three Canadian models just don't suggest anything of this sort. There's a bullseye of 19 from the high resolution. The global is struggling to put anything above 5. So really deficient comparison. This is telling. So this is a bouncing back and forth between radar and 1 hour outputs from the high resolution, and just you can see how poorly the forecast was handling the 1 hour precipitation amounts. It has these little skinny echoes of some convective showers, I guess, as opposed to this big blob of extremely heavy precipitation. And that's every hour between basically it's a 12-hour animation from that morning 13 Zulu on the 21st to that evening 0Z on the 22nd, and this continued beyond 0Z on the 22nd, well through the night into the next day. So. And then just a means of comparison. So all of the model outputs that I've just shown are, as I said, raw model outputs. They're also not convective allowing models. They do parameterize the convection. Just to show a comparison, there is a HER the HER model is actually a convective allowing model. And it in particular, I'm not going to say all of the convective allowing models were suggesting such high amounts, but this one in particular did have some very high amounts through central Nova Scotia, the 10 to 15 inch range. It's a huge, it's a very, the 5 to 10 inch range. Some a little bit more. The last minute forecast actually backed off a little bit, unfortunately, kept it under 10 inches, which is about 250 millimeters. I mean, for this little area, it's got a huge range of precipitation. It can be anywhere from 125 to 250 millimeters. But just to say, it really did have a signal of some quite a bit, considerably heavier precipitation for this convective output. So that's kind of what I was able to find. So then development got involved and they did some tests. They took the HR to the high resolution. They're thinking if any of the models might hopefully catch it would be the high resolution model. They wanted to see how the new implementation, the new version model upgrade that's going into effect very soon, how it would handle the situation. So they did more tests than what I've got displayed here. They've got some with deep convection, without deep convection active. They acknowledge that it did predict about up to about 140 millimeters of precipitation. So it's an improvement. It's certainly better than having a problem predicting anything exceeding 100 millimeters, as I had mentioned earlier. So it's better, but the question, of course, is can it predict more what we saw? So we have yeah, that's the bullseye there, the yellows there near Lunenburg. That's actually pretty well placed in terms of where we saw a bullseye, at least towards the coast. It was near that Bridgewater area that received 260 millimeters. So it's got 140. Again, it's better, but it's still not giving enough. So certainly an improvement. Even when they went to the 1 kilometer, they did get some amounts exceeding 150, but failed to exceed 175. So just to say, the new model probably, if it had been operational at the time, it might have performed better. But the conclusion was it doesn't seem that it would have produced enough. And then just on this map here, there is a bit of terrain just to kind of show the effects of terrain over. It's not extremely terrain. It's not like there's a mountain range across Nova Scotia, but there is a bit of terrain through the spine of the province. So the summary was basically like, yes, that's basically what I said. The summary was that, yes, it's better. The new forecast is better. There were some things we could have done, but none of these tests were significant enough to predict even 200 millimeters of precipitation. So then the question became, they were starting to wonder about water vapor being assimilated. So now I'm switching over to an observation. So this was a radiosonde launched at 0 Zulu on July 22nd. So it was the evening of the 21st. So there's a little bit of a warm nose just off the deck. There was wind coming right off the water, which would have a low level marine inversion. Then otherwise it was unstable. And it was saturated right up to basically the freezing level. And the winds were very unidirectionally off the water here in sheer water. And it had a non-surface based convection, implying with a CAPE of near 1800 joules per kilogram in this area here. And it noted a precipitable water of 48 millimeters right here.
Less than 1 minute, please.
Okay. Okay, so yeah, so the GDPS or the three models were not too bad actually when it came to verifying that one unique point. But the GDPS was about 47 millimeters, right along the edge of this plume. One thing that they wanted to point out though was that where the balloon was launched was actually not within the plume; it was maybe on the edge. So the thought is that the thought was that the precipitable water within the plume in reality might have been considerably higher than 48. So it was more chance that the balloon launch happened to match fairly well with what the model was saying, because indeed the model, while it might have said that was right, it certainly didn't have the precipitation. So the suggestion was that perhaps the model should have had a way higher precipitable water amount within the core of this plume of moisture. And then just to finish off, there were some comparisons from that morning with some precipitable water soundings, and there was a bit of a deficiency from the analysis, noting there was both of them were about too low. Both of the analyses were too low compared to the soundings from Yarmouth and Shearwater that morning. So the question is, of course, was everything upstream also under analyzed, and if so, by how much? So I'll finish there. Basically, to summarize, none of the convection parameterized models, foreign or domestic, were able to forecast enough. A convective allowing model, and like the HER in this case, performed quite a bit better. The high resolution deterministic system, the Canadian, did a much better job, but it was still not significant enough to predict enough precipitation. And the suspected cause of the under forecast amounts is poorly assimilated water vapor. And that's a known challenge for numerical weather prediction systems. So yeah, I'll stop there. Thank you for your attention.
Thank you very much. I see one question online. It says, perhaps the CAPE and vertical motion ascent was unpredicted by all the models?
Because I did comparisons of the deep. My supplementary notes are going to have anything about that. Convective parameterization. I have to look at the most unstable CAPE. I don't know that it was considered. That's something interesting that I can bring up to the group.
There's one more question real quick. Could you comment on the hydrometeor drift effect in HRDPS as compared with in the GDPS RDPS?
Yes, well, that was pretty apparent, at least for the comparison between RDPS and GDPS. Sorry, go back to that. I know I don't want to take too much time. This guy, you can really see the effect of the hydrometeor drift here in the GDPS. I'm not sure why you can sort of tell it's there too in the RDPS, but especially in the GDPS, you can really see the effects of I would say the lack of hydrometeor drift. And I have no qualms about saying that definitely had an effect on not bringing the precipitation amounts far enough inland, contrary to the HRDPS, which has a different parameterization and handles the hydrometeor drift much better.
Great, thank you so much.
Thank you.
It's a great presentation. We will move on to our next speaker. Our next speaker is Yeechian from McGill University. Please go ahead and share your screen.
Hello, everyone. So I'm gonna get started here. So everybody, thanks for the introduction. I'm Yeechian, and so this is part of my PhD work, supervised by Professor John Gyakum at McGill University. So I'll be talking about influence of Rossby wave and jet stream patterns during extreme precipitation regimes or EPRs in Eastern North America. And we're also funded by FRQNT and NOAA. So to motivate this study, long-lived and widespread extreme precipitation periods often lead to flooding. So this example here on the right is from February 2019. In particularly extreme case, we had a long period of very long period with multiple precipitation events, and so we had a lot of flooding in, say, Tennessee and other areas of the southern U.S. and Ohio Valley, Mississippi Valley, and then farther north, there was actually like record snowfall across here in this picture in the upper Midwest, in the upper peninsula of Michigan. So, and also lots of snowfall also across parts of Ontario and Quebec that time as well. So like precipitation in general, so forecasting such periods is a significant challenge still, and we find that extreme precipitation research is generally focused more on shorter duration events like a day or two, or single events, and not so much of clusters of multiple events lasting, say, 5 to even 15 days. So how do we actually get long-lived periods of precipitation or heavy precipitation? Well, in the mid-latitudes, especially in the cool season, heavy precipitation usually is produced by mobile transient mid-latitude cyclones. And so you can have either one storm that is kind of quasi-stationary over a region, or we can have multiple going over the same region in quick succession over a short period of time, like in this example here in the storms hitting California in December of 2021. So that actually gets me to the persistence of weather patterns in general, since, well, these kind of like long wave synoptic to continental scale weather patterns, say like the 250 or 500 hectopascal flow patterns, are modulating jet streams and storm tracks, and to get either like a quasi-stationary storm or even like a series of storms, we need to have like a persistent storm track that's kind of stationary, persistent. And we find also that the storm track itself, because of the moisture transport and the condensation of all the moisture in the cyclones and releasing latent heat, that these can actually feed back into the circulation and kind of into the whole synoptic scale pattern and help sustain their storm track, like in a positive feedback loop. And so some ways to measure, well, one way to measure persistence is just like the speed of the individual troughs and ridges in upper level wave patterns. So we can see here an example on the right, the persistent cold extremes over winter, December through February, have a CP or a phase speed that's rather low, not even 2 meters per second across Europe, whereas the short-lived extremes have more like 4 or 5 meters per second. So even though like the amplitude, which is actually shown in the black contours, are not really that different. So but both of those are there. They play an important role. Both amplitude and phase speed play important roles in the magnitude and persistence of such extreme weather. So now I'm going to define extreme precipitation regimes, or EPRs, and they're basically a period of at least 5 consecutive days, allowing for one-day breaks where we have a large heavy precipitation, so a very unusually large amount of precipitation, like in this area here, which I call Eastern North America, this shaded region. So that includes the most populated area of the Eastern US and Southeastern Canada. And so I'm using the area 5 so winter, December to February, and from 1940 to 2022. And I'll be happy to answer more questions about any details about and more details about what goes into this afterwards, and there are also some in the paper listed below as well. The other okay, so there's also the concept of Rossby wave packets, which are generally which are concentrated areas of Rossby wave activity and are kind of are where most of the so a lot of this energy in this Rossby wave patterns, drifts and troughs are kind of concentrated in RWPs. And we use this algorithm here to calculate some of the properties such as amplitude, and focusing here on the phase speed in this presentation. And that's using the 250 meridional wind anomalies, so upper level wind anomalies. Using that methodology, I actually had 132 of EPRs, so 132 cases. And what I'm showing now, I'm going to get into some results here, is a composite over all of 132 cases. So an average of all of them. First, I'm going to show in the bottom left, like a time average over the whole EPR life cycle and over all the events. So the shading here indicates the 250 hectopascal high anomalies. And so we see a little bit of ridging in here, South Alaska. We have troughing in Western North America, ridging in Eastern North America, and then the meridional wind anomalies are contoured. So we have the dashed contours indicating negative values and solid contours indicating positive values. And so the main takeaway from this, and here's the green boundary for Eastern North America. So the main point is here we have a lot of southerly flow here. A lot of moisture, so that's favorable pattern for a lot of moisture transfer from the Gulf of Mexico into this region, and also this area east of the synoptic scale trough and west of the ridge is a favorable area for ascent and cyclogenesis. And so we got both. We got the moisture, and we also got ascent to condense out the moisture and dump its precipitation. On the right, we have same thing except it's a Hofmahler, so it's instead of a time average here, it's actually average over latitude. So this over this magenta region, latitudes 30 to 55 north. And now we're going through the life cycle of the EPR, time going this way, longitude going that way. And so these green dashed lines indicate the longitude bounds of Eastern North America. So this is here and here. And we have about, say, start -3 days, so 3 days before the start of the EPR, and then going up to the start in this dashed dotted line. Dotted line is the end here, and then we got like the midpoint, and then after the end. And so the main point of this is that, well, we do see this kind of ridge trough ridge structure, right, throughout the EPR, but we also see that beforehand it's kind of displaced to the west, and it moves eastward into this kind of favorable pattern when it starts, and then it kind of just stops moving. It's kind of just stationary there, and it doesn't really until near the end when it starts to kind of move eastward and out again. So the time average shows you the favorable pattern, generally speaking, and then the top model shows kind of the pattern persisting over a long period of time. So here I'm showing similar thing, but with precipitable water and shading and integrated vapor transport vector here. So this kind of, I guess, just confirms what we see about this IVT's moisture coming right out of the Gulf of Mexico in this region. We also see some moisture transport in the Central Pacific as well. And we see also in the Hofmahler that initially, before the start, we don't actually have a lot of moisture, so relatively low values of PW. But then once we get the southerly winds going from the Gulf of Mexico, and then we start to see more moisture expand throughout the whole Eastern North American region. So these are the bounds here. And then again, it's kind of moving, and then getting kind of get pushed off to the east by the end. So here I am showing the phase speed and phase speed anomalies by the Rossby wave packets. And here I'm just mainly focusing here on the kind of these blue areas here, and here indicating anomaly slow anomalously slow moving Rossby wave patterns or basically weather patterns. And so we see that we see kind of that's the most pronounced actually during the EPR itself in this Hofmahler between the start and the end, and not so much present before and after, at least in the immediate like EPR region, Eastern North American region in these green lines here. So, and also this measure of phase speed also is it actually filters out some of the short wavelength features. So we could have actually like a series of storms that move relatively quickly, but don't really change the whole long wave pattern very much, and that would still count as a relatively like slow phase speed. Okay, so here on the bottom left, what I'm showing is the percentage anomaly of the fraction of time width in which the 500 hectopascal height anomaly is at least 75 meters for a 10-day period or longer. So that's basically just a measure of very persistent ridging in a particular area. And we see that this anomaly here is up to say 0.07. And so the climatologically, it may be up to 0. The climatological value is up to 0.1. So you add 0.06 or 7 to it, that's kind of saying that it's occurring maybe 1.5 or 2 times more often than climatologically. So we see a lot of ridging, persistent ridging out here that confirms with our the kind of the 250 hectopascal height anomaly of positive height anomaly south of Alaska. And we also see a little bit of that in the East Coast region as well. So, and on the right here, I'm just going to focus on this kind of brown area here, this brown contours, which indicate negative potential vorticity of action by the irritation of winds at 300 to 200 hectopascal layer. And that just means that we got latent heat release, and that's just in ridge buildings. So we got these storms tracked. We have a storm track like this, and storm track like this here. And we saw the integrated vapor transport like this and like this. And so that actually, when the moisture condenses out and then it releases latent heat, and then it kind of actually helps build a ridge on the western sides of, actually helps build a ridge on, say, the western side of this ridge here and this ridge here. And then you have this latent heat release and ridge building on the northwestern sides. And that actually helps slow the progression down. It's not allowed to just move eastward quickly if it keeps being rebuilt on the western side. And so that's actually, so the storm track itself is actually helping to contribute back to kind of this persistence of this pattern in that way. So just to quickly summarize, so we have slow moving Rossby wave pattern to configured to transport a lot of moisture from the Gulf of Mexico and actually Western Atlantic to some degree as well into Eastern North America, and that is contributed by a lot of ridging in the Central North Pacific, especially, and also to some extent near the East Coast of the U.S. And with the storm track itself and the associated latent heat release contributing to the persistence. So yeah, so thanks for listening. I'll take any questions now.
Great, thank you so much. Are there any questions online? Yes, here. When you say RWP moves very slowly, is this based on phase velocity or group velocity? Does the downstream energy propagation help slow down the system?
Okay, so I was actually referring to the phase velocity here. So like here, so like I said speed, but yeah, it's basically phase velocity. And I haven't really looked at the group velocity, and the algorithm itself, it kind of it makes it look kind of noisy, and that's a little bit less of an issue with the phase speed, but the group velocity seems kind of noisy, and I'm not really sure what to make of it. So yeah, I haven't really investigated that, but yeah, that might be interesting though.
Excellent. Any other questions? Right. Apologize if there's any delay, but feel free to ask questions in the online chat, and I encourage the speakers to check the chat and reply to any additional questions there. Thank you very much. We will move on to our next speaker is John Gyakum from McGill University. Please go ahead and share your screen.
Okay, can people see this?
Yes, it looks great.
Okay, so my talk today relates to intrusions of subtropical air into mid-latitudes of North America during the wintertime. I'd like to thank my co-author, Yeechian, whom you just heard. He's a multitasker, so he does a lot of different things. And this topic is only marginally related to his. And I'd also like to thank you to my sponsors as well. So what I've got here are two examples of an extreme case of, let me see if I can move this away and up. Let's see here. Just get rid of this. That helps a little bit. These are two soundings related to ice storms in Montreal. First, the one on the left is from the Great Ice Storm of 1998. And what we see here is cold air below, northeasterly channeled winds along the St. Lawrence River Valley with a very strong inversion between 700 and 800 hectopascals. And then the other sounding is actually from last April of 2023, in which we also had a devastating ice storm, surprisingly so. And the equivalent potential temperature that's maximized between 900 and 700 hectopascals was about 322 Kelvin. And as we'll see later on, that's about 30 Kelvin above the wintertime climatology for Montreal. During the April 2023 ice storm, and this is not an isolated event in the sense of the transports that we often see, to achieve such a large value of theta E, of 319 in this case, during April of 2023, we see at low levels there was a transport of air from the planetary boundary layer of the Caribbean into the Gulf of Mexico and straight up into Montreal, and this is very typical of what we normally do see. And that facilitates essentially a sounding, and we saw soundings earlier today, but this is a pretty typical of a wintertime extreme precipitation event in which the temperature profile is pretty much saturated right along the moist adiabat. The extreme precipitation events in the St. Lawrence River Valley are often associated with subtropical air. Now let's consider the idealized anticyclonically curved trajectory from lower latitudes into the St. Lawrence Valley. This is an anticyclonic gyre around a particularly strong anticyclone, subtropical anticyclone in the North Atlantic Basin, and it's transporting very warm theta E air into this region. This is the climatology of the equivalent potential temperature, not at one particular pressure surface, but rather the maximum equivalent potential temperature that we find between the layers of between 700 and 900 hectopascals. And you can see our climatology in southeastern Canada for January is about 289 or 290 Kelvin. And what we're seeing in these extreme events is something like 320 to 322. That's Montreal. And so what we've done here is to identify the synoptic and dynamic environments that are associated with extreme theta E maxima with a threshold of the 99th percentile. This based upon finding the climatology of these max theta E values during the period from 1991 to 2020. As we'll see later on, climatologies are kind of moving targets in this age of climate change. So we'll have to be careful about that. So what we did in this exercise was to examine on this map 3 sounding stations at approximately 45 degrees north: Salem, Oregon, Aberdeen, South Dakota, and Maniwaki, Quebec. And we're looking here in particular at these 3 stations. The threshold for these 3 stations is not all that different from one another, about 312 Kelvin at the 99th percentile level, with precipitable water associated values of 24 millimeters, about an inch in Salem, Oregon, in the middle part of the continent, at Aberdeen, South Dakota, 15 millimeters, and at Maniwaki, about 18 millimeters. The data set that we're using is the ERA5 hourly data at a resolution of about 1/4 degree latitude longitude for the winters of, in this case, 79 through 2021 to 2022. We've since updated the entire data set from 1940-41 through the last winter of 23 and 24. We'll give you an example of that later. Now, why do we use this one metric at one level? the maximum equivalent potential temperature? Well, first of all, theta E is a conservative quantity in the absence of diabatic heating and turbulent mixing. So air parcels that transport this quantity are transporting it conservatively from one location to the next, in general, in the absence of convection in particular. So the lower tropospheric theta E maximum represents the base of the tropospheric coupling index, which is kind of a poor man's convective stability metric from the perspective of potential vorticity reasoning. Furthermore, extreme equivalent potential temperatures at the base of the precipitation layer are particularly susceptible to extreme precipitation rates. And I've italicized P here. This represents a rate. I've taken this from Chuck Daswell's paper dealing with ingredients for extreme precipitation. What's lacking here is the duration. I'm not addressing that today, but what we are doing is looking for the precipitation rate, which represents the vertical integral of the vertical velocity, the ascent, times essentially the air mass, the change following an air parcel up along a moist adiabat of the saturation vapor pressure. Now, what we've done for the number of cases that we've looked at, and I'm going to show you 2 stations only at this point. Salem, Oregon, 71 cases from self-organizing maps, and we're looking at 9 different members or 9 nodes. And so among these 71 cases, 53 of these had measurable precipitation, and the numbers that you're looking at here represent 6 hourly amounts. The top left node is one in which we have relatively dry conditions, a median value of only 3 precipitation events of 0.5 millimeters over a 6-hour period. And the wettest one is the one on the bottom, which we're going to focus on some, 14 cases in which 13 were precipitating with a median amount of precipitation depth of 7 millimeters over a 6-hour period. Now, what you see here are anomalies of thickness, 1,000 to 500 hectopascal thickness. It's not a surprise by any means that we have anomalously warm tropospheric temperatures. What we do see in the bottom right is in the dash contours, we are seeing the anomalies of sea level pressure. And so if you look carefully here, we are dealing with anomalously strong southwesterly geostrophic flow right from the North Pacific Ocean directly into the west coastal areas of North America. And if we follow this, these air parcels that you see here from the high split trajectories are coming in from low latitudes, the subtropics of the North Pacific, and traveling directly into the area of Salem, Oregon. These air parcels are furthermore lifted near the location of the precipitation. And I refer you to the sounding, which again is very much like a moist adiabat and saturated. So this idea of equivalent potential temperature, I think, is a really good one because it's broadly representative of theta E, which is essentially constant through the troposphere under these saturated conditions. Here, the theta E max is 319 Kelvin. We've seen that number before. The same results from these self-organizing maps are shown here, in which we have the ERA5 precipitation amounts, and in particular, the bottom right node is showing us particularly heavy precipitation right along the coastal areas of North America in association with this atmospheric river from the subtropics. The one on the upper left in particular is largely dry because this is related to an anticyclone with descending air, potentially warm air coming in, but relatively dry, still giving us a large value of equivalent potential temperature. Now, if we go eastward to Maniwaki, Quebec, in which we have 59 cases, among these we have 54 with measurable precipitation amounts. The wettest one is shown here on the upper left, in which we have a deep and anomalously strong Great Lakes cyclone with southerly geostrophic flow in over the area of Montreal and Maniwaki. The median values of 6 hourly precipitation are quite substantial, 11 millimeters or so. And what is going on here is that, as we saw in the previous soundings, we typically have channeled near surface flow right along the St. Lawrence River Valley, channeling cold air with aloft the very large values of tropical moisture coming in from the south. The bottom right is the driest, essentially one of the drier nodes that we look at, primarily because there's the deep cyclone. Any type of cyclone is parked way off to the west of Lake Superior, with the circulation dominated by a subtropical anticyclone. Now, the self-organizing maps have shown us here the precipitation amounts. And what's really intriguing about this is that for these top left and top right nodes, what I've done is I've outlined with an oval the St. Lawrence River Valley. And if you look carefully at these pictures, the maximum value of precipitation is oriented right along the St. Lawrence River Valley, where there seems to be a measurable increase, a marked increase in precipitation focused directly over this low elevation area. In conclusion, extreme values of lower tropospheric maximum theta E are characterized by anomalously warm thicknesses for 1,000 to 500 hectopascals. That translates into about plus 15 degrees Celsius of anomalous warmth. These self-organizing maps distinguish crucial synoptic dynamic structures that facilitate relatively dry versus wet, the distinguishing of relatively dry versus wet events. Now, the question is, are these cases of extreme theta E's really subtropical air mass intrusions? And the short answer is yes. For Maniwaki, as an example, if we use the metric of air parcels over a 72-hour period that travel from lower latitudes south of 30 degrees north in the Caribbean, the Gulf of Mexico, or the Gulf Stream current of the North Atlantic, 52 of the 59 air parcel trajectories ending in Montreal traveled from this region. For the case of Salem, Oregon, of these 53 cases with measurable 6-hourly precipitation, we had all of these tracking to the subtropical Pacific. The remaining 18 cases that I've pointed out in Salem that were dry were associated with descent in anticyclonic flow. Now, this is an analysis, and maybe appearing to be a rather busy looking chart, but what we have here is the precipitation depth over a 24-hour period. And the x-axis shows us the equivalent potential temperature numbers. And again, though this is for 900 hectopascals, it doesn't much matter because theta E is mixed through the troposphere. And what we're looking at here is in these regimes in which we're looking at extreme values of theta E between 321 and 330 Kelvin, there's a large sensitivity to even the smallest increase in rising motion from 1 to 5 centimeters per second. This sensitivity is illustrated for this maritime tropical air mass, in which for the 1 centimeter ascent, very marginal amount of ascent rising motion gives us like 7 millimeters over a 24-hour period. Whereas for the case of just 5 centimeters per second in this air mass, you get well over an inch in a 24-hour period. So we're going to be looking at the dynamical impacts of increasing extreme values of theta E on frontal circulations and cyclogenesis, also on similarly structured frontal zones, and also synoptic and planetary circulations, and also on moist convective systems. One point that I'd like to make here, just to look at a longer term time series from an 84-hour period, we see Salem, Oregon on the left and Halifax, Nova Scotia on the right. And if you just plot 84 points representing the number of hours of extreme theta E values, you see in terms of looking at a trend, it's kind of a marginal upward trend. But I think what's pertinent about this is that in more recent years, we seem to be changing the climate, and particularly so in Halifax, where during the last decade, we had upwards of 5 separate events of greater than 40 hours of theta E maxima exceeding the 99th percentile over this 30-year period of climatology, which precedes us right now. So this is a big deal because it facilitates the likelihood that we have more extreme precipitation events increasing in time. Thank you very much, and I'll ask if there are any questions.
Great, thank you very much for that presentation. Are there any questions from the audience? Perhaps I'll ask one while we wait to see if any come in through the chat. Can you comment on the sample size that you need for the self-organizing maps analysis? How many cases do you need to do that?
I think what we have right now, that's a good question, was on the order of 70 cases or so. And we have since done self-organizing map for for double the period, and we're getting about 110 cases. And there seems to be a robust lack of sensitivity to these numbers in any case, because I didn't show this, but the results of these self-organizing maps with 9 members show us essentially the same results over this 84-hour period as opposed to the 40 or near 50-year period that I just showed you in this presentation.
Great, thank you. There's one question from online. Is theta E conserved diabatically?
Yes, it is. It is definitely conserved for moist condensation processes in which you have large-scale ascending motion. So in other words, if you have precipitation occurring, stable precipitation occurring, equivalent potential temperature is definitely conserved. When it's not conserved is when you have moist convection taking place with turbulence.
Great, thank you very much for that presentation. We will move on to our next speaker. Our next speaker is Thabo Mpanza from York University. You would like to go ahead and start sharing your screen, please?
Okay, can you confirm that you can see my screen?
Yes, we can.
Okay, thank you. Thank you, Chair, for the opportunity. My name is Thabo at York University. I'm working with Professor Tandon, doing my PhD. So today I will talk briefly about differences between convection-parameterizing and convection-resolving simulations of future changes in extreme precipitation intensity over the subtropical regions. So maybe the first question will be, what is responsible for a decrease in extreme precipitation intensity? So if we look at figure 1 now, which is the composite climatic change in 10 years of daily omega, which has been normalized by a zonal mean climatic change of surface temperature. And this is mainly for the summer season, your JJA. So from this, the warm colors are showing you the weakening of extreme ascent of omega, and then the cold colors are showing you a strengthening of omega. So from this, you can see that there is a lot of uncertainty or weakening that is associated with this parameter. And we can associate this parameter with the dynamical part of the system, as we know that we have the thermodynamical component and then the dynamical component. So this will be representing the dynamical component. So if we go to literature and then we look what's there in terms of EPRs and climate change, it is well established that in a warmer climate, the moisture content of the atmosphere is expected to increase following glacial chaperone at about 7% per Kelvin of warming. And generally, that will enhance EPRs because we'll be having a lot of moisture in a given column of the atmosphere. So greatest uncertainty comes from the subtropical regions where my study is focusing at, and then that uncertainty is mostly associated with the dynamical effects. Fall and Tandon 2017-18 respectively associated this variability in EPRs with extreme ascent, where extreme ascent is defined as the large-scale vertical velocity during an extreme precipitation event. So how do we connect extreme ascent with extreme precipitation? We'll go through this popular quasi-geostrophic equation. It is a linear equation. So on the left, I've got 3 terms, which we call the forcing terms. Then on the left, I've got the Laplacian. So if you see the color coding there, term number 2 is differential vorticity advection, term number 3, temperature, and then term number 4 is diabatic heating. So this is a diagnostic equation. So given a 3-dimensional flow, which is geostrophic, you can sort of quantitatively estimate extreme ascent. So this expression has been expressed in this way specifically to show the effect of some of the terms. For example, you can see the L over there, which is representing the effect of eddy length, and you can also see N squared over there, which represent the effect of stability. So in earlier studies, there has been suggestion that stability as well as the eddy length are playing a key role over the subtropical regions. An increase in stability on its own will weaken extreme ascent, so that will be the atmosphere being resistant to vertical motion. How do we do these experiments? So we adopt a framework called the Calum quasi-geostrophic framework. I will go through just figure 3 of this busy slide. I think it will summarize everything that is here. So the starting point is a driving GCM. In this case, it's KNSM2. And then from KNSM2, we extract the large-scale forcings, which are applied uniformly across the domain. And then those forcings are the advective tendencies of absolute vorticity, temperature, as well as moisture. We also get surface boundary conditions in terms of SSTs, latent heat, as well as sensible heat fluxes. And we also derive some vertical profiles of moisture as well as potential temperature to nudge the CRM towards that. So on the right, that's where I've got the CRM. CRM is capable of resolving convection explicitly. So when the CRM resolve convection, we are going to be able to calculate Q, which is your convective or your diabatic heating. And then from that, now if we've got Q, if you remember the equation I showed you, we can now fully specify it or fully resolve it for large scale vertical velocity. Then once we've done that, then the cycle sort of repeats itself. And we do have this very important parameter, which is the eddy length. It is tunable, so you can tune it, decrease it or increase it. We compute this from the omega fields from the GCM at 500 hectopascals, and then we sort of prescribe it to the model. So what's unique about this is that the coupling between convection and large scale is captured via diabatic heating, which is missing in most conventional dynamical downscaling. So the first experiment that we ran, we call these experiments isolation experiments. Basically what you're doing is you're running the model but only modifying one parameter or only introducing a perturbation or a climatic change. And then the result that you get from that will be associated with the parameter that you perturbed or the parameter that you modified. So if we go through figure 6 here, on the y-axis, I've got intensity, millimeters per day. On the x-axis, I've got time, day 1 up to day 11. And then what is demarcated by the dot here, that's where the extreme event was. And the blue colors, that is your historical climate. And then the red color, that's your future climate. And then the yellow color is the perturbation or the isolation experiment. So before I go through this, I need to make a remark that the CRM is underestimating these intensities a bit when we compare it with the GCM, of which it is more or less expected, since the GCM that we're talking about here parameterizes convection, and the CRM that we're working with sort of resolves that explicitly. Also, even though there is that underestimation, we're not concerned about that, because the thing that we're looking for is that is the CRM able to capture the decrease from the historical climate going to a future climate. So if you compare these curve, the blue and the red, you can see that there is a decrease. So that's the key character for this model, that it's suitable to continue with the runs. Also, I do run a single column model, which is also showing the same character. So now, if we come back here, the first isolation that we did was the eddy length. The second one was stability. The third one was absolute vorticity. So from this, you can see that both the eddy length and the stability are producing a decrease in extreme precipitation, but absolute vorticity is producing an increase. So this experiment is done over a central part of Manitoba, and we're specifically focusing on the summer season here. So it is going to be June, July, August. So we had issues with the model not being stable here, and then we ended up resolving that by specifying the surface fluxes, which is your latent heat as well as your sensible heat. So this is a bit unique from what we've been obtaining in other locations, but I'll talk more on that later. So if we now go take a closer look at the advective terms only of that omega equation, we have temperature advection, we've got moisture, and then we've got vorticity. In this case, we see that if we perturb temperature advection, we do get that decrease. We do capture that decrease. If we perturb vorticity advection, we also capture that decrease. But if we perturb moisture, we get the opposite, which is an increase. This might make sense since, as you saw in the first slide, that we do expect the moisture content of the atmosphere to increase. So that might be the factor resulting in this increase over here. So again, if I compare this with the other results that I've got so far, this is unique when I compare it with the single column model, where the single column model is showing the opposite here, where the single column model will be showing moisture advection as the dominant term in terms of decreasing this extreme precipitation. Also, other locations that we've tested over ocean, over the subtropical region, showed that absolute vorticity advection has the dominant effect across all the locations that we tested over the subtropical ocean. So here I'm just going to show you more or less the same experiments, but this is coming from a single column model which parameterizes convection, and it's a work in progress. I don't have results for single column over land yet, but this is over ocean, subtropical ocean. So again, everything is the same. The first experiment is length, isolation, stability, and then advection. So what you see here is that all the terms, they are responding to the decrease in extreme precipitation, which is unique compared to what the CRM is doing. One special character that we observed with this single column model was that all the precipitation that we're getting doesn't come from the parameterization scheme. So it's only gives us like your large scale precipitation. So that's the unique character that we're able to find, and this sort of resemble what is happening in the GCMs, because also when we're doing an analysis and comparing this with the GCM, also we saw that with the GCM, mostly the precipitation comes from the large scale. There is very little that is coming from the parameterization scheme that deals with convection. Again, this is from the single column model, but now it's the advective terms of the omega equation. And then this is what I was talking about, that moisture advection tends to be the dominant term in terms of the decrease in extreme precipitation when we're dealing with a single column model. So one thing that I also maybe need to mention, these are ensemble mean. So for this one, I've got about 9 ensemble members. And then for the land location that I showed earlier, I've got 5 ensemble members. And then in conclusion, the CRM ran successfully over land, which had previously given us a lot of issues with stability, but it did run after we specified surface fluxes. The decrease in intensity were well captured, even though there is an underestimation. Eddy length, changes in eddy length and stability are playing a role, especially for that location over land, which is in line with what Tandon and others found in 2018. Advection of vorticity is not playing a key role over land location, opposite to what the ocean locations were showing. Also, all the precipitation from a single column model does not come from a convective parameterization. And this is similar to what we see when we sort of analyzing precipitation from a GCM, Kenneth M2 in this case. So the next step, I would like to increase the sample points over land, and also just to make the results to be more robust, and also compare and contrast the results of the single color model over land, which is what I'm working on. And then I'll sum it up with sort of putting everything together in terms of which mechanism is dominating at which region. Yep, that's all I have. Thank you.
Great, thank you very much. If there's a quick question, we probably could do that. Let me see if there are any coming in. Okay, not yet, but I will move on for the sake of time, but I will encourage anyone to keep adding questions in the online platform, and I would encourage you, Thabo, to please check the online platform if there are questions you can respond to there. So thank you so much for that great presentation. We'll move on to the final speaker of our session is Kenneth Chow from Environment and Climate Change Canada. Please go ahead and share your screen.
Is that showing up?
Yes, it looks great.
Perfect. Let me arrange everything. Yep. So yeah, thank you everyone. No, it's late in the day, so yeah. So my name is Kenneth Chow, and I'm from the Canadian Centre for Climate Services at Environment and Climate Change Canada. I'm here today to showcase some of our work in developing snowfall projections for Canada using the novel CAN-DCS M6 dataset by our partners at the Pacific Climate Impacts Consortium. But before we get started, I want to acknowledge that I am presenting today from Ottawa, the traditional and unceded territory of the Anishinaabe Algonquin Nation. So a bit of background. Over the years, many users have come to us at the CCS requesting information on future snow and snowfall so they can use this information and data in their decision making. Ultimately, we lacked downscaled and bias-adjusted snowfall data that would be useful to these practitioners and users. Now, with the limitation of temperature and precipitation data alone, snowfall can be calculated from these variables. Most commonly in literature, it's done using a threshold of 0 degrees Celsius. Anything over may be considered rain. Anything at or lower this threshold would be solid, so it's snow. While projections could have been calculated using the downscale data that we currently serve on our data portal, climatedata.ca, it is ultimately a univariate downscaled data set that doesn't account for intervariable relationships during downscaling and bias adjustment. However, our partners at the Pacific Climate Impacts Consortium, or PCIC, has recently developed a new multivariate downscaled set of projections, and we sought to use these to estimate snowfall, kind of a low-hanging fruit, so to speak. So the Canadian Downscaled Climate Scenarios Multivariate CMIP6, or the M6 for short, is a multi-model, or consists of a multi-model ensemble of 26 CMIP6 GCMs. Has SSPs 126, 245, and 585, and recently developed and provided SSPs 370. It uses a new peak blend gridded historical target used in downscaling and bias adjustment. Has simulations of daily minimum temperature, daily maximum temperature, and daily total precipitation. And it's downscaled and bias adjusted using the climate imprints and the multivariate bias correction and PDFT methods. But before we dive straight into calculating snowfall from GCM simulations, we wanted to determine how we were going to determine and derive snowfall from these daily simulations. In lieu of other variables other than temperature and precipitation, we focused on 3 threshold solid precipitation estimation methods. These are documented and are part of the Canadian land surface scheme that feeds into CANESM. Of course, there are more complicated and complex regression type formula and energy balances. But again, as we're only limited to temperature and precip variables, we focused on these. There's the binary method, which I mentioned previously. There's the Brown method, where the fraction of snow decreases from 0 to 2 degrees Celsius. And then there's the hour method, which is a polynomial between 0 and 6 degrees Celsius. What complicates this further is that these methods don't specify between mean, maximum, and minimum daily temperatures, as they're generally applied on sub-daily data. Thus, we also had to verify which daily temperature variable to apply as well. So to evaluate them, we first focused on observational or the adjusted homogenized Canadian climate dataset. So we derived daily snowfall using each of those methods I described for 3 temperature variables that were available from the AHCCD data, and then using precipitation to derive the snowfall. And then we compared them to the AHCCD observed snowfall data. We looked at 300 stations across Canada with at least 20 years of valid data from 1970 to 2010. And we filtered stations and considered them valid or a year valid should they have no missing days of data during the months of October, November, December, January, February, March, and April. This criteria is derived from the WMO standards for precipitation climate normals, but we relaxed them a little bit to focus solely on the months where snow would generally occur in Canada, generally. And then we looked at metrics such as mean bias, mean squared error, and Perkins score for all of the 9 configurations. Perkins score is a bit more uncommon, but it is the measure of the fraction overlap between the distributions of the data sets. So the closer to 1 means there's more overlap. So what's shown here are the 2 highest performing configurations. The showcasing maps with stations across Canada, and the average of the metric across all the stations is noted on the bottom left of each of the maps. So comparing the hour method using daily maximum temperature, and the Brown method using daily mean temperature. Overall, the hour method that uses daily maximum temperature has a slightly lower mean bias and root mean squared error, RMSE. However, both configurations performed well in terms of Perkin score. Just from the margin alone, we ended up deciding to go ahead with estimating snowfall using the hour method and with daily maximum temperature. So moving on to the M6 simulations. On top of calculating daily snowfall, we also calculated a number of climate indices that we thought would be potentially useful for users. And these are total snowfall, annual or monthly, number of days with snowfall above 2 millimeters, days with snowfall above 10 millimeters, and maximum 1 day snowfall. These were chosen as total precipitation climate indices on climatedata.ca were available. So we chose these to emulate what users would be also provided when the data is disseminated on climatedata.ca. And you may notice that I'm using millimeters here as the snow data is in millimeters of snow water equivalent. One thing we wanted to check was that since these indices were not downscaled and bias adjusted directly, we evaluated them to ensure that they were not anomalous or erroneous. So here are Taylor diagrams summarizing how well the model simulations aligned spatially with the gridded target in the historical period of 1981 to 2010. These diagrams indicate the Pearson correlation, the standard deviation, and the RMSE between the simulations and reference. And overall, the derived indices for all GCM simulations aligned very well with the PKIC blend target. So indicating there's nothing immediately peculiar with the data sets. As for the projections themselves, here is a time series similar to the ones a user would see on climatedata.ca, showing total annual snowfall projections from 1950 to 2100 averaged across Canada. In black is the modeled historical simulations. Blue would be SSP 126, green would be SSP 245, and red SSP 585. We haven't extended the work to SSP 370 as of yet. The lines indicate the 50th percentile of the multi-model ensemble, whereas the shaded regions indicate the 10th to 90th percentile ranges. In orange is the PKIC blend historical values, just for reference. While SSPs 126 and 245 don't indicate much change, SSP 585 sees a considerable decrease in the total annual snowfall by the end of the century, with the lower 10th percentile indicating a quite extreme decrease. Now, ultimately, these are averaged across Canada, so for a more regional look, these are maps showing the modeled historical 30-year average of annual total snowfall for 1971 to 2000. The bigger map is the median, while the smaller maps are the 10th and 90th percentiles. Here is the change in snowfall by the end of the century, 2071 to 2100 for SSP 126 and for 585, specifically just these two to get a look at the bookend scenarios, so to speak. And we can see from the figures in the median that Northern Canada will see a slight increase in snowfall, while the Atlantic and Pacific regions will see a decrease in total annual snowfall. when looking at the 10th and 90th percentiles, we can see that there is a variability between the model projections in that there are models that show a decrease for parts of Canada in the lower percentiles, while there are models that show increases. So for example, in northern Quebec region, there is an increase in snowfall in the 90th percentile for both SSPs 585 and 126, whereas in the 10th percentiles, there are decreases. Other parts include Baffin Island and Central Canada. However, there is an agreement across all the percentiles that there will be an increase in snowfall in the north and decreases in the west and east. As for the snow season, we wanted to look at whether or not the snow seasons will be shifting. So this is the historical climatology of monthly snowfall for 1971 to 2000. Snow tends to ramp up in the fall and plateau in November, and then decreasing in February. However, by the end of the century for SSP 126, there seems to be an observable decrease in snowfall in October, but increases in December, January, and February. This becomes more and more apparent in the higher emission scenario. So this is 245. And this signal is very prominent under SSP 585. This can be attributed to the CAN DCS-M6, wherein it projects increasing amounts of precipitation. And although temperatures are increasing, especially for the high emission scenario, or very high emission scenario, there will still be months where it is, or months and years where it is still cold enough where the fraction of snow is non-zero using the hour method proposed. So in summary, this was a snapshot of our work on deriving snowfall projections and associated indices using the CAN DCS M6 dataset. Changes to snowfall and snowfall indices were most prominent in Eastern Atlantic and the Western Pacific coasts. And snowfall is projected to decrease considerably in the shoulder months, whereas it will increase in the winter months. Increased variability may be due to increasing precipitation, but a shorter snow season. So there's a decreased signal, but in years that are still cold enough, high snowfalls may still occur. So thank you very much for your time. And yeah, if anyone has any questions.
Great. Thank you very much for that presentation. And thank you to everyone who is still online. I'm so glad to see so many of you have stuck around to the very end. I'm not seeing any questions yet in the online Q&A. So perhaps I will just say a couple reminders, and if one of those pops in before we're done, then I can give that. So on behalf of the other conveners of this session, I want to thank you all for coming. We had 6 very nice presentations today, so a virtual round of applause to all of our speakers. A reminder that we have 2 posters in the poster session on Wednesday. And then this is the end of our current session. There is one more session tonight, the public lecture that starts in just under half an hour. I don't see any more questions online, but I encourage anyone that has additional questions for our speakers to contact them either through the event platform or by email directly. So thank you everyone for coming. I will go ahead and end the session here. And I look forward to seeing you at the rest of the conference.
Thank you very much.